All right, so let's get right into a KVL example. I'm gonna give a circuit with a sinusoidal voltage source, throw a resistor, an inductor, and another resistor in there. And let's just call this R1, L1, and R2. Let's give some values here. Let's call this Vs of t. And let's say that my problem asks me to determine I of t in this circuit. Okay, so what we need some resistor values, and we need an inductance, and then we need to know what our sinusoidal source looks like as well. So let me give those parameters. Let's say that R1 is going to be equal to 1 kilo ohm. Let's say that L1 is equal to 1 millihenry. Let's say that R2 is equal to, let's say something like 3 kilo ohms. And let's just say that F is equal to 100 kilohertz. Okay? And so if I were to, and let's say that Vs is equal to, this is capital Vs, this is the amplitude of my sinusoid. That's going to be, let's just say that it's 5 volts. Okay? So I want to know what I of t is in this circuit. I have all these parameters here. Let me actually just throw a box around them. Why not? And then we can just move them somewhere a little bit more convenient if we need to. Just throw them up here. So if I'm going to write out my Vs of t, I can write it as, we know that it's going to be Vs times the sine of omega t. There's no phase for my source. Let's just say that my phase is 0. So I'm going to say that that's going to be equal to 5 sine omega t, which is 2 pi times 100 kilohertz times t. Right? That's going to be my Vs. And let's go ahead and write our impedances. So that's going to be the first step here, is kind of to convert over to the impedance domain. I'm going to replace my resistor, my inductor, and my second resistor with their associated impedances. Okay, so this one's going to be, we'll call it ZR1. That's just going to be the resistance of my resistor, which is just going to be 1 kilo ohm. Same for R2, that's just going to be ZR2. We'll call that one 3 kilo ohms. And then for my inductor, it's a little bit trickier. We remember that the inductor's impedance is actually dependent upon frequency. So it's going to be ZL1, which is going to be J times omega, which is 2 pi times F, right? 2 pi times 100 kilohertz, times L, which is 1 millihenry. And I already put that in my calculator in advance so that I could just write it out. That's actually going to just come out to J times 628.3. Okay, so that is our impedances. Now we can use KVL this is Vs of t, which we could also write as a phasor, but I'll get there in a second. So let's go ahead and just write our KVL loop. We're going to start at this point, and we're going to go around the circle, or go around the loop this way. So my first term is going to be going from minus to plus across Vs of t, so I would write Vs of t. Then I'm going to drop across this resistor, so I would write minus I of t times 1k. Then I'm going to drop across this impedance of this inductor, which I would write as minus I of t times J 628.3. And then I have another drop across my other resistor, which is going to be minus I of t times 3k equals 0, right? So I've written my KVL loop. And now we have all these I of t terms, so we could factor out an I of t and kind of group these terms. Let's say Vs of t minus I of t times 1k. I've got a plus 3k in there, and then I've got a plus J 628.3. Those are my terms here. That's going to be equal to 0. And now I can group the 1k and the 3k because those are both real numbers. and I can move this entire term here over to the other side by adding, right? So let's do that. I'm going to be left with Vs of t is equal to I of t multiplied by 4k plus J628.3. Okay? And so now all I have to do to find I of t is I have to divide Vs of t by this complex value here. This is my impedance. This is the series impedance, right? This impedance right here. I talked about how impedance is basically real part, which is the resistance, plus J times the reactance in my circuit. Well, if I combine my three elements in series here, I've got one here, and one here. I can see that those three elements in series, I just add their impedances. 1K and 3K gives me 4K. And then the inductive impedance is going to be frequency dependent. So that one is distinguished by the fact that it's multiplied by J, right? This is my reactance in the circuit. So the series combination of these three impedances gives me this impedance here. And we can see Ohm's law pop right out of KVL, just like it did last time. So this is my impedance Z here, and I'm looking at V is equal to I times Z, just like Ohm's law tells us, right? And so in order to solve for I, which is what I'm looking for, I just need to do I is equal to V divided by Z. But how do I do that, right? I have Vs of t over here, which is a function of t, and I have Z, which is a complex number. How in the world am I going to do that math? Well, I'm going to reserve that for the next video. This problem is kind of all set up. And now we're going to use what we learned about phasors and complex numbers, and we're going to go ahead and solve for I of t and complete this problem, okay? So let me go ahead and end this video right here. And in the next video, we're going to do the necessary math to solve for I of t, okay? I'm going to have to go ahead and stop this video.